All right, let's start. Okay, so last time we finished at maturity. Okay, so we talk about how to calculate the maturity, which basically is areas underneath the temperature and time curve. Okay, but also the maturity method has its limitation. Okay, for example, here two concrete uh, has the same maturity does not necessarily mean they have the same strength, as we can clearly see from here. Okay, same maturity, but the strengths are different. Okay. So next, let's talk about the test for absorption and permeability. So these tests are pretty much similar. So basically, is see how much moisture or gas the concrete can absorb, okay, by capillary suction, okay, because this is a good measurement of concrete quality, okay. The lower the permeability, the less absorption, the concrete will be more durable, okay, because the aggressive materials will have harder time to penetrate the concrete. Okay. And lower value of absorption will indicate these aggressive ions will have harder time to penetrate into the concrete and do the damage. Okay. And here shows what are the factors affecting water absorption values. Okay, so many of them we should know them already. So if we reduce the water cement ratio, we have less porosity. Okay, as a result, the water absorption will goes down. Okay, if we increase the curing time, also we increase the alpha. Okay, so we increase alpha also means we reduce the porosity. So again, the absorption value will goes down also. Uh, Decrease the curing temperature. So that means the growing of the hydration product will be slow. So we have more homogeneous hydration product. So in the end, when alpha approach 100%, we will have less, uh, porosity. So the water absorption will also goes down. And also increase degree of consolidation. So we have better consolidation, we have less porosity, so that will also reduce the water absorption. Similar things for permeability. So we mentioned about permeability many times in early lectures. Okay, so permeability or permission. Okay, so describe the mass transport of liquid or gases induced by either the pressure as a water head or concentration gradient. So you have a gradient in concentration, difference in concentration into part of the concrete, then that will may push the transportation of the liquid, the ions to move. And also by capillary force, the suction of the capillary force. Okay. And permeation, the permeability is affected by the volume as well as the connectivity of the capillary pores. Okay, so the volume of the capillary pores is quantified by the porosity. Okay, so which is defined as the volume of the pores divided by the volume of the total materials. Okay, so that's one thing. The other thing is the connectivity of the capillary pores. That's basically how well the pores are interconnected to each other. Okay, that is also important. One example for that is, remember we talk about aerated concrete, which is the concrete has a lot of isolated pores, which is made by hydrogen gas. So we put the powder of alumina, then it will react with hydroxide ions. So that will generate hydrogen gas and other stuff. Okay, so this hydrogen gas will generate these air bubbles, which reduce the density of the concrete. So we call that aerated concrete. For this concrete, although the porosity is very high, but the pores are not interconnected each other. So when you put the concrete in water, it can float on the water. So that means the density is very low, and also the pores are not interconnected. So anyway, the volume is important, but the connectivity is also important. Okay, sometimes the connectivity will change the porosity, the permeability quite a lot, even though the porosity itself is pretty high or low. Okay. All right, and these slides talk about permeability and the moisture content of concrete. Okay. The moisture content of concrete has a big effect on concrete permeability. Imagine we have moisture inside the pores, then the other material will have harder time to get inside. Okay. So the air permeability of concrete will increase when the moisture is eliminated. When you oven dry the concrete, the pores will be dried out. So it will make the air easier to penetrate the concrete. Okay. This will in turn also increase the connectivity of the pores because the channels between the pores will opens up when we dry the moisture from the pores. Okay. And here it says the water absorption also increase when the capillary pores are empty. So when we dry out the pores, the water will also have an easier time to be absorbed by the concrete. Okay. So moisture content has a strong effect on both the permeability and also water absorption. Okay. All right, and here shows one of the tests. This is the surface absorption test, absorption of water. Okay. This is the water reservoir. Okay, we have tap here which can open or close the valve. Okay, this is the sample of concrete. The test measures the water flow into the specimen. Okay, goes through a known surface areas. Okay, the surface area is well controlled. Okay, and the test is affected by moisture condition, how much water is inside the concrete, okay, and also the cleanness of the surface. Okay. We can use this method to measure the water absorption under field condition. Okay, so we can measure how much water is absorbed by the concrete. There's some other tests such as RCPT test, okay, which is rapid chloride penetration test. This is one of the ASTM standard tests for the permeability of concrete. Okay, but there's some other tests which we can use to measure the water absorption and also the permeability of concrete. But today we just talk this. Okay. All right. So next, we're going to talk about stress wave propagation method. All right. Okay. All right. So first of all, let's look at what is wave. Okay. Now here is the definition of wave from Webster dictionary. Okay. So wave is disturbance of variation that transfer energy, okay, from one point to another in a medium. Okay. So this is transfer of energy in a certain medium. All right. And the energy could be in the form of, for example, elastic deformation. Okay. So this is the case in, for example, the sound transfer in concrete. If you use a hammer to pound the surface of the concrete, so the hammer will transfer elastic deformation of the concrete as a form of wave. Okay. Or a variation of pressure. Okay. For example, wind. Wind is result of pressure gradient in different location of the air. Okay. And also it could be in the form of electric or magnetic intensity. Okay. When we talk about, I remember we talked about GPR. No, no. This is GPR is for ground penetrating radar. Okay, so which we'll discuss in next lecture, I believe. So GPR is using EM wave, okay, electric or magnetic intensity. All right, or electrical potential, okay, as a voltage, for example, or even temperature difference. Okay, so these are some form of energy. Okay, so energy is transferred in a medium. The medium could be many things, okay, such as concrete. We use a hammer to pound the concrete. The concrete will be the medium here. Or when I talk, we have sound wave. In that case, the air will be the medium. Okay. For EM wave, okay, it can be transferred in even vacuum. Okay, so medium could be also many different options. Right. So that's the general definition of waves. But in this class, first we're gonna talk about mechanical wave. All right. For a wave, we have different definition: the period, wavelength, and amplitude. Okay, so I think most of you know this already, but let's review it. So the amplitude A is the maximum displacement for a certain wave. Okay, and period T is the time between two successive wave crests. Okay, for example, this is one crest, and this is the next crest. The time difference between these two successive crests is called period T. Okay. And wavelength is defined as distance between two successive wave crests. Okay. This is the curve for distance and displacement. Okay. And here is amplitude, and the wavelength is the distance between two successive wave crests, and we call that lambda. Lambda. All right. And when you use a hammer to pound the concrete, okay, let's see, we use a hammer to pound the concrete, and if you send not only one wave but several waves, okay, so let's say here is the point of impact. Okay. All right, some waves are reflected only near the boundary. Okay. And for that wave, we call that R wave, okay, or surface wave. Or Rayleigh wave. Okay, the same thing. So this is one of the wave transferred only at the boundary between one medium, which is the concrete, and the other medium, which is air. Okay. We have at least two other type of waves. Okay. One is called air wave or longitudinal waves. Okay. So longitudinal wave is transferred in all direction into the medium. Okay. Also, we have transverse wave, okay, or T wave. Okay. So T wave also transfer in all the directions. Okay. So what's the difference between longitudinal wave and transverse wave? Before we do that, let's mention the longitudinal wave has the highest velocity. The speed of these three waves are different. L wave has the highest velocity. Okay, and the surface wave or R wave has the lowest velocity. Okay. Then let's look at the difference between the L wave and the transverse wave, the T wave. Okay. So here is the L wave. Okay, that's a our other name. One is called compressive wave, also called R wave. This wave is caused by compression of the elastic materials. Okay, and also that's another name is called primary waves or P wave. Okay, so let's look at this is direction of excitation. For example, we use a hammer to pound the surface of the concrete. So let's focus on one of the particles. You see the particle is moved from left to right. And the wave's direction is also from left to right. Okay, so this is direction of travel of the wave is the same direction as direction of the particle motion. Right? Okay. So compression wave is caused by elastic response to compression. Okay, so let me write this down. So compressive wave caused by elastic response to compression. Right. So as long as the medium has elastic response to compression, compression wave can be propagated in that medium. Okay, and here shows the governing parameters for compression wave, which is, as you can imagine, the E value, which is modulus of elasticity, and also the density. Okay. If you increase the E value or increase the density of the material, the medium will increase the velocity of the compressive wave. Okay. So again, any medium has elastic response to compression, compressive wave can be propagated in there. So it can propagate in solid, liquid, and gas. The shear wave is also called T wave or transverse wave. Okay. It is caused by elastic response to shear. Okay. Again, we have excitation here. The direction of the travel is from left to right. Okay. The direction of the particle motion, if we focus on one, is from up and down. Okay. So direction of particle motion is perpendicular to the direction of the wave. And that is caused by, again, elastic response to shear. The materials need to be able to have an elastic response to shear so shear wave can propagate in that medium. Okay. As a result, shear wave can only propagate in solid, such as concrete or soil, but it cannot propagate in liquid and gases because liquid and gases cannot provide elastic response to shear. Okay. And the speed of shear wave is governed by shear modulus, G, and also the density of the materials. All right. Yeah, let me know if you have any questions about this. Okay. So let's continue to talk about the wavelengths, speed of the wave, and also the frequency. So last time we talked about lambda. Lambda is the wavelength. Okay. V is velocity of the waves, okay. And F is the frequency. And probably you already know the frequency of the wave is equal to 1 times t, okay? Because frequency is how many cycles within 1 second the wave can go through, okay? Which is equal to 1. 1 is equal to 1 second divided by period. Period is, again, defined here as the time between two successive wave crests. Okay, so this is basic acoustic. Frequency is equal to 1 over t. Right? And frequency is material property. Okay, so which means, frequency, not frequency. Wave velocity is the material properties, which means no matter what is the wavelength of frequency, the velocity does not change based on period and frequency. Okay, which means if we use a hammer to pound the concrete, the speed of the mechanical wave in the concrete is fixed, no matter what is the frequency of the period. Okay, so that is what the wave velocity is a material property means. Okay. The frequency has very wide range, okay, from infrasound, which is less than 15 hertz. Okay. The audio sound range is between 20 to 20,000 hertz. Okay, so that is frequency human being can hear. Ultrasound is from 20 kHz to 1 gigahertz. Okay. And beyond that is called hypersound or microsound. Okay. The dog whistle, okay, give you an example of ultrasound is within the range of ultrasound. Okay, and some animals can also use ultrasound to communicate, such as elephant or whale. Okay, they can use a very low frequency infrasound to communicate. So this is outside the audio sound range. So human being cannot hear that, but infrasound can travel a long time. Okay, so that's how we can use infrasound to communicate with over a very long distance. Okay, so for NDT, normally we use ultrasound range, okay, which is between 20,000 to 1 gigahertz. And here is a reason. Okay. One is ultrasound wave in concrete travel kind of slow. Okay. And also the ultrasound wave can easily penetrate opaque materials. Okay. So this is depending on the wavelength of the ultrasound, which we'll discuss in a moment. And also the equipment to generate ultrasound is not very expensive. Okay, so that's the reason people normally use ultrasound to check concrete materials. All right. The next slide, this slide is very important slide showing us how the frequency will affect the penetration and also the resolution of the test use ultrasound. Okay. So if we increase the frequency, so if we increase the F, okay, so then the wavelength will be smaller. So that will reduce the wavelength. Why? Because remember the velocity will not change, constant. Okay. So if we increase the frequency, we're going to reduce the wavelength because again, the velocity will be constant, right? So reduce the wavelength will translate into better resolution, okay? Which means the sound can detect smaller flaw, okay? So which is good. However, the energy will be dissipated faster. As a result, the wave cannot penetrate very deep. So this is bad. Okay, so this is good, this is bad if we increase frequency. If we use lower frequency, we're going to have higher lambda, okay? And as a result, the resolution will be smaller, which is bad, okay? Because the wavelength is higher, it can not detect very small flaw. But the energy will be dissipated less likely, much harder. As a result, the wave can have a larger penetration, which is good. Okay, so increased frequency, we have better resolution, but we have smaller penetration. Reduced frequency, we have better penetration, but we have smaller resolution. Okay, so which frequency we use actually is a question of balance between the resolution and penetration. Okay. For example, in concrete, the frequency of 200,000 hertz is normally used, and the reason for that is because the velocity of mechanical wave in concrete is around 4,000 meters per second. Okay, and the frequency is 200,000 kHz. Okay, and from there we can calculate the wavelength. The wavelength is around 2,000 meters divided by 200,000 hertz. Okay, so which is around 0.02 meter. Okay, so 0.02 meter is about 3/4 of an inch. All right, so 3/4 of an inch is about the size of the coarse aggregate in concrete. Okay, remember in the coarse aggregate is around 3/4 inch or half inch. Sometimes is 1/2 inch. Okay, the reason we use the wavelength about the size of the coarse aggregate is because if the wavelength is smaller than the coarse aggregate, the wave cannot easily pass the aggregate. So as a result, the wave cannot penetrate deep enough inside the concrete. If the wavelength is too large, it can easily pass around the coarse aggregate, but the resolution will not be as good. It cannot detect smaller flaw. So that's the reason we use 200 kHz, because in that case, the wavelength is around 2 centimeters or 3/4 inch, which is about the size of the coarse aggregate. Okay. All right, and then let's look at a couple of ultrasound techniques, machines. Okay, so this is one of the instrument. As we can see, we have two parts. Okay, so one part is send the wave, the other part is to receive the wave. So the receiver and the generator, the sender, are two separate parts. Okay, so we call that the wave transmission method. Sometimes the transmitter and the receiver will be in the same unit here. Okay, for example, here is the materials we want to check, which is the steel plate in this case, and this is the medium which will make sure the wave will be reflected. Okay, so we want to check, for example, the thickness of the steel plate. So we'll send the wave here, okay, and the wave will be reflected back. Okay, and based on that, we can measure information such as the thickness of the steel plate. But here, again, the transmitter and receiver are in the same unit. Okay, so we use the wave reflection method. All right. So this is one of the method which is called UPV. It's called ultrasound pulse velocity. Okay, the transmitter and the receiver are on two ends of the materials. Okay, if we can measure the thickness of the materials, we can easily measure the time difference between we send a signal and the signal is received. Okay, and based on that, we can calculate the velocity of the wave inside the concrete. And that's a pretty weak correlation, but positive trend between velocity and the strength. Typically, if the concrete has higher velocity, the strength will also be higher, but the correlation is not that strong. For typical concrete, the velocity is around 3,500 to 4,500 meters per second. Okay, if, for example, we have large voids here, okay, and then the wave will have take much longer time to go from one end to the other. So that will greatly increase the time. So the velocity calculated will be much lower. So we can use that to monitor the uniformity of in-place concrete. Okay, for example, we have column here, and one area we have, honeycomb here. So we take the measurements at many ends. Okay. So if the concrete is homogeneous, all these measurements will have a similar result. But here, the velocity will be much lower. So we say probably we have some internal flaws here. Okay. Here says the UPV method is not very reliable with opposing side. So we're going to use the wave transmission method, not the reflection method. And here is a table based on what is calculated velocity. We can give a general condition assessment for the concrete, okay, between excellent, good, to poor, to very poor. Okay. So this is the ultrasound pulse velocity method. Okay. Here is another method use ultrasound. This is the transmitter and the receiver are in the one side. Okay, so the wave can propagate through the materials from the transmitter to receiver. The distance can be measured, and also the time interval between the signal is sent to the signal received can also be measured very accurately. So we can measure the velocity depending on the distance and time. Okay. We can also, move the receiver to different positions. Okay, and we measure the distance between the receiver and the transmitter, and also the time. Okay, so from there we can draw the curve of any point. So this is distance from the transmitter. This is the time which we can measure or calculate it accurately. And the slope of that curve will be 1 over velocity. Okay, so based on that, we can calculate the velocity of the wave transmitted in the material. And sum of wave is based on reflection or refraction or reflection. Okay, and we need to talk about the famous Snell's law. Okay, let's say we have angle. We call that incident wave. This is the wave, and this is the medium interface between two materials. Okay, so material 1, the velocity of the wave will be v1. The wave in the second materials will be have velocity of v2. Okay, so part of the wave will be reflective back. Okay, and we know these two angles, theta 1 will be equal. Okay, some of the wave will be retracted. Okay, which is into the second materials. Okay, but the theta 2 will be different from theta 1. Okay, and there's a correlation between this theta, which is here. So sine theta 1 over sine theta 2 is equal to v1 over v2. So that is the famous Snell's law. And that special angle is called first critical angle, which is defined when a longitudinal wave moves from slower to a faster materials. Okay, so this is faster material. V2 will be larger than V1 because the theta 2 is larger than theta 1. Okay, so V2 will be larger than V1 based on this equation. Okay, so because theta 2 is larger than theta 1, if we increase the incident angle, we increase theta 1, theta 2 will also increase. Okay, at a certain point, theta 2 will be 90 degrees. Okay, so the wave will be like this. Okay, so theta 2 will become 90 degrees, and we call that angle of theta 1 is incident angle or first critical angle. All right, so let's see if we have transmitter here and receiver here. All right, and this is two materials, material 1 and material 2, and V1 will be less than V2. All right, so let's see if we move the receiver from here to here. All right, and we can measure things. One is the x, the distance between the receiver and transmitter. Another one is the signal. Okay, the time between transmitter send the signal to the time the receiver receive the signal. And there's a two paths here. The path 1 is the easy path, which is the direct distance from transmitter to receiver. And another path is here. Okay, so when the angle is equal to critical angle, the theta 2 will become 90 degrees. So the wave will transmit here and then shift it back to the receiver. So this is another theta 2. And pay attention, here is the thickness of the material 1. Okay, so based on this information, we can calculate the thickness of material 1, the h. Okay, This is how we do that. Again, we plot two curves. One is the pass one, another one is pass two. Okay? And x-axis is distance to the transmitter. Okay? For the pass one, it is very simple. Okay, so we increase distance between transmitter and receiver, so the curve will be linear, and the slope of that curve is 1 over v1. So based on that, we can calculate the velocity of the material, the wave in material 1. And same thing, we can calculate the velocity of the wave in material 2, v2. But this is the pace 2 at time 0, okay, which is when the distance of transmitter and receiver is 0, is here. So the traveling distance is just go down here and go up there. So because of that, when the distance is 0, we have time ti, okay? So which is a function of velocity and the thickness of material 1. Okay, so based on this information, we can calculate thickness of the material. All right, so this is anyway an example of how to use ultrasound and the reflected wave to measure certain things, such as the floor, okay, or thickness of the materials. All right. So yeah, that's the end for the lecture today. Hold on a second, let me see.